you probably printed that on your own. Let me just show you this. Rohypnol. Sometimes called a date-raised drug. It's a short-acting hypnotic. Has a nitro group. Okay, it's on the pre-course worksheet. Long name flunitrazepam. It's got a fluorine, it's got a nitro group, and it's a diazepam. It's a benzodiazepam. Similar to Valium. But that's one drug that has a nitro group. Not a lot of drugs have nitro groups, but some do. Okay, EAS. We just looked at nitration. Form nitronium ion. Tell me if you like those lights on and off. Off. I think so too. Okay, nitration. We did it in the lab last week. This week in lab, we're reducing the nitrate to the amino. Very common two-step sequence to get an amino on the aromatic ring. The nitro can be reduced with a couple of different ways. One common way is to use an active metal, such as iron, tin, or zinc. Those are the three most common. There's other ones. And a proton source. In lab, you have a choice of either zinc or tin. Iron just doesn't work out quite as well, I've found, and it also stains the glassware. I don't know why. I've used iron before. Common proton sources, your typical acids. Sulfuric, acetic acid will even work. You can even use like base salts like ammonium chloride, some type of proton source. Obviously, you got to have two H's to get on the nitrogen. The oxygens come off as water, so ultimately I think you need 6 H's. Okay, you produce 2 moles of water during the reaction. We're not going to look at any mechanism. It's called a dissolving metal reduction because, oh, it's not really. Because, well, sometimes. Base metals are not soluble, but it forms, the iron gets oxidized to an iron salt, and typically that's more soluble. Problem is, and I'll make a comment about the lab, is you got to get rid of the iron salts. If they're soluble, they're not going to stay soluble when you add water. That's because they're going to form hydroxide. Iron hydroxide, tin hydroxide. If you know your solubility rules from Gen Chem, the only hydroxides that are soluble are typically like group 1 and sodium hydroxide. Metal hydroxide is typically not soluble in water. That's why, like yesterday we were doing the extraction, the metals salts just won't dissolve in anything, neither the ether nor the water. And if you want to separate your phases, you have to filter those out. Metal hydroxides are notoriously very fine and hard to filter out. Do you all agree? Yeah? Okay. Y'all learned this in Gen Chem? Yeah? Today I want to see if we can make a couple of changes to the filtration. Also, when you're filtering, you guys just don't have enough working experience to know some little tricks to do to get things to go faster. That's not your fault. There are a variety of ways, but the filtration did go slow yesterday. Let's see if we can do a couple of things to try to speed it up today. But it is a struggle to get rid of the metal salts sometimes because that's a byproduct. You can also do this with hydrogen. Just like an alkene or an alkyne we reduced with hydrogen, you can also reduce nitro groups with hydrogen. Standard precious metal catalyst like palladium or nickel. That's an alternative way. It's actually very nice. You don't have the problem of the filtering out the salts. We can't do that in lab because we just don't have the setup to supply gas hydrogen to you. We do have a hydrogenator in one of the labs. I can show you that at some point. One year we even actually did a kind of a group. We combined some nitro from several students and we did this one time. Okay, when dissolving metal reduction, we're not going to show mechanism, but please remember that any of your active metals, you treat them with acid, they'll get oxidized and they'll produce hydrogen. Now, I'm not saying that they produce hydrogen and then the hydrogen reduces your compound. It's probably a direct reduction, but keep this in mind. Okay, any questions about reducing nitro to amino? Most common way to get a amino group on a ring. Look on the flip side, you'll see a drug that has an amino group over here. First off, anybody recognize the compound without the amine? That's thalidomide. I gave you a handout about thalidomide organic 1. Remember thalidomide? What did it do? Caused birth defects back in the early 60s, mainly in Europe. Well, now an amino on there, and they're using the same compound now to treat some blood cancer. So thalidomide does have a rebirth a little bit in terms of treating cancer. Other substituents. Next reaction. Sulfonation. Take benzene and you can put on a sulfonic acid. Okay, that's a condensed structure. Here's your true Lewis structure called benzene sulfonic acid. You can do this with SO3 and sulfuric acid. Sulfuric acid is going to be, I believe, a catalyst. SO3. Let's see if we can draw a Lewis structure for that. Boom, boom. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 5. Actually, that right there works if you expand the octet of sulfur. 2, 4, 6, 8. 12 electrons are on sulfur, but that's okay because it has d orbitals. We could also maybe do a resonance structure where we move these out. Make that minus, and this is plus. It still has an expanded octet. It's still more than 8 around it. You can move it out one more time and make that 2 plus and 2 minuses. Then you would only have 8 around sulfur. But really, any of them work. If we use this structure here, the ring is going to attack the sulfur because it's bonded to the sulfur. Okay? We have a positive sulfur here. Typically, though, you need an acid catalyst. This species is, what's the net charge of the species? Neutral. Neutral. But if we protonate this guy here with our H plus catalyst, that there? Is that right? We now make a cationic species. Now this is apparently electrophilic enough that the ring will attack it. Now see, this here has lots of donation to the sulfur. And so it's really quenching that positive charge. Now the oxygen doesn't donate as much. So the sulfur's left there with, hey, I need some help here. Well, in comes the electrons here, attack here. Really nothing has to leave here. You just attack the sulfur because it can expand into octet. What does that give? We attack sulfur. It's got double bond to O, and what else? OH. There you go. There's your sulfonic acid. And now the sulfur is neutral. There is an H here, plus here, standard sigma complex. After we attack the electrophile, now something can take the H. Well, there's a minus floating around here, yeah? What's the minus? That, or water, because it's an aqueous acid, you can use water, but I typically use the anion. These electrons in, restore the aromaticity, until you get that, and what do we reform? We reform H2SO4, which acted as a catalyst to make our SO3 more electrophilic. Benzene sulfonic acids are not that common, although you put a methyl here, the pair position. With the methyl there, it's called para-toluene sulfonic acid. Does that sound right? It's kind of a blend name. I mean, it's really, it's not named as a toluene, it's sort of named as a, you could call it paramethyl sulfonic acid, or you would say paramethyl benzene sulfonic acid. So it's sort of a blended name. But what do we know this as? PTSOH, pyritosol acid. PTSOH is a solid acid. I don't think we've used it before. We've used tosyl chloride. That's just where you replace the OH with a chlorine out here, the tosyl chloride. The tosyl acid is this, and it's a dry acid. I don't think we've used it before, but we'll see it later where we want to use a dry acid. And since it's dry, it also implies it's a solid. And solids are often much easier to work with in lab because if you spill them, you can sweep them up. And as opposed to a liquid, you spill it, well, you got it everywhere. Just easier to use solids in lab. Especially if you're doing a lot of work and just. So we will see tosyl acid. Sulfonation is actually reversible. You can take benzene sulfonic acid, heat it with H+, and you can get benzene and you can release SO3. That's just the opposite of what we did up there. I mean, you could draw an equilibrium error where up there we reacted these two with H+ and they came this way. You can actually go the other way. If you go the other way, that is, you start here and go here. What is the electrophile if you go that way? What does the ring attack? It attacks the H+, because there's a new H. There's a new H here. We've got to get a new H there. Can a ring attack an H+? Yeah. Sure. I mean, end of yes. We attack the S+. We attack an I+. You attack an H+. Somehow you got to get the SO3 off. I like you to try to do that reverse mechanism on your own. All it is just moving electrons to get where you need to go. You know where you need to go, so just draw out the electron movement, and that's what we call a mechanism. It's pretty straightforward, but it is an example of an EAS where you're not replacing an H. In this case, you're actually replacing an SO3 H group. Because of that, SO3 groups can be used as what we call a protecting group. It doesn't mean too much to us right now, but later on we'll see what a protecting group is about. Basically, you can sort of put the SO3 group on, do chemistry, and then take it back off. And with the SO3 group on, it sort of directs your chemistry while it's on, and then you get rid of it. Okay. Please try to work that mechanism. We'll see protecting groups a bit later. Okay. Okay, let's think about what we put on a benzene ring. We put halogen on a benzene ring. What else have we put on? Nitro, which is a nitrogen, form of a nitro. Sulfur we just did. Okay. Oxygen we will not put directly on a ring. It's actually pretty difficult. It's better to do it using diazonium chemistry, which replaces an amine with something. What else could we try to put on a ring? We've already done halogen, nitrogen, sulfur. Oxygen, just told you we can't really do. What else could we do possibly? You'll put a carbon on the ring? Yes. That's going to be called Friedel-Crafts chemistry, and there's a separate handout for that. Okay? We'll put carbons directly on the ring. And that's going to be about it. You're talking about bonding to a carbon? Really try to just focus in on the atom. If it's a carbon-carbon, then yes, then it's probably going to be called a Friedel-Crafts. At this point, though, we're going to kind of take a little side detour to a very important topic. Then we will come back to the Friedel-Crafts, which is putting carbons on the ring. Before, we need to learn a little bit about the reactivity of the ring and substituent effects. That is, if you just react benzene, you can put the one group anywhere because all 6 carbons are the same. But if you react, for example, toluene, and you try to put a bromine on, for example, if it goes here, that's different than here. Because here it will be ortho to the methyl, and here it would be para, or there would be meta. So you've got 3 different positions it can go. So what we have to see is, how does the methyl influence the chemistry you're going to be doing? And that's called a substituent effect. What is the effect of the methyl? And there's 2 things we're going to be looking at. Roman number 1 is reactivity. Does the methyl make this more reactive than if it was not there, than benzene? Or with the methyl, is it going to make it less reactive? We have to be able to answer that. So that is called activation, deactivation. And that's what we're going to look at first. And we're going to look at a variety of groups and how they deactivate or activate. Roman numeral 2 will be directing effects. That is, where does this direct the bromine to end up at? Ortho, meta, or para. So we're going to look at what each group, how each type of group directs. First, though, is activation. Okay, if you have an electron donating group on the ring and it donates in, partly net, because a lot of times a group can both donate and withdraw. But it usually doesn't do it the same. Maybe it's a weak donator and a strong withdrawer. So net, it would be called a withdrawer. What is its net effect? If it's a net donating group, it's going to make the ring more reactive than benzene. I assume you can read that or you see it on the sheet. I'm not going to try to move every single time. If you have a net electron withdrawing group, it's going to be less reactive than benzene. This mainly comes down to sort of what I alluded to when we introduced EAS. That is, what's the charge of the intermediate in EAS? What's the intermediate called? Yes. Yes, I also call it a sigma complex, okay? You're making a carbocation intermediate in your EAS reaction. How do you stabilize carbocations? Do you donate or withdraw? You donate. So if we have donating groups, is that going to stabilize the plus? Yes. And that will make it more easy to form? Yes. So donators are going to make it more reactive. Because donators stabilize the positive that you form. Hopefully this is going to be pretty straightforward. And most of the stuff we're going to do is just going to go back to resonance and donation effects, induction, just, okay? We're going to be applying what we should already really know. Now, if you have a withdrawing group here, is that going to stabilize the plus? So it's going to make it less stable. It's going to make the ring less reactive. It's going to be less willing to form your intermediate. Question, Kevin?
If you have multiple, like if you have an electron donating group and an electron avoiding group.
We'll have to look at multiple groups. We'll do that. Yeah, sort of at the end, we'll move to that. Okay. Well, what I just explained is shown here with these reaction coordinate diagrams. Here's a ring that has some type of donating group. Here's your cation. Because it's donating, this is going to be more stable. Here's benzene. Okay, nothing on here. So it's at a certain level. Donation is going to lower this down. So it's meant to be a little bit lower than that. Because this is lower, typically your transition state energy leading to that is going to be lower. That's usually what sort of the assumption we make. On the other hand, if you have a withdrawing group when you make your sigma complex carbocation, it's going to destabilize it, and so it raises it up. If it raises it up, we assume that the transition state leading to it is going to be higher. That's going to be more difficult, thus slower reaction. So hopefully you found that pretty straightforward. The chore, though, is understanding the net effect of each type of group. Okay, for example, methyl. I think you really already know what the net effect of a methyl is. This just goes back to carbocations. Is methyl going to be a donator or withdrawer? Donator. Donator. I mean, we learned that a long time ago. Iodine is more reactive than benzene. But the methyl stabilizes the cation. Okay, let me ask you this. Does it stabilize it by resonance or by induction? Induction. Induction, yeah. It doesn't do resonance. It has no p orbital. Okay? Well, let's go through these. Some of these will be new because we'll see some new groups. But we'll just have to rationalize, okay, well, yeah, that makes sense. Hopefully you'll be saying that. Types of groups. Now, I group mine into 4 different groups, Roman numeral 1 through 4. Some textbooks, or most actually, group a little bit differently. And actually, one of the handouts I give you is a little bit differently. My group 1 is going to be called strong activators or donators. They strongly donate electron density, and thus that activates the ring. And so it's same term, really. What atoms are these? These are going to be atoms with long pairs other than halogen. And the most common, thus, are going to be oxygen and nitrogen. Atom with a lone pair other than lone halogen. Now, does this mean that you can't predict others? For example, sulfur. Would you think sulfur is a group 1 based on this definition?
Yes.
No? Hopefully you think it would, because does it have a lone pair?
Yeah.
Is it a halogen?
No.
Yeah. So it should fall into this definition. Okay? These are strong activators, donators. Okay. Yes, these atoms are more electronegative than carbon. Here's an example. Thus they withdraw by induction. If you drew a dipole here, you would have a dipole that looks like that, correct? And so that's a withdrawing. So that's an inductive effect. Alternatively, or however, this can also donate by resonance. Okay? And so we can also do this. That sort of implies resonance there, and we can draw resonance structure. So it can do both. But it turns out that their donation by resonance is very strong, and it's thus the predominant overriding effect. So even though these groups can withdraw inductively because they're more electronegative, that's a minor effect compared to the donation by resonance.
Would it make a difference if there's a double bond to the oxygen?
What do you mean, double bond to the oxygen?
Like, not necessarily on this compound, but on a compound, would it still be a donator if there was a double bond to oxygen?
You can't have a double bond to oxygen, because then this carbon would have 5 bonds. I think you may be thinking of a ketone.
Yeah.
Well, you can't have a ketone directly to a carbon ring of a benzene because it has 5 bonds.
If it was in like a benzylic carbocation location, or
Okay. Well, let's look at that. So you want to show a compound like maybe this?
yeah.
Okay. Is the ring bonded to? Does this have a lone pair?
No.
Okay. Is this an atom with a lone pair?
So it's directly bonded to the
Okay.
ring.
Yeah. We're not talking about this type of atom right now. I mean, there's no lone pair there, so it's not a group 1. Group 1 is atoms with a lone pair, other than a halogen.
Does anything past the first atom out make a difference?
Slight difference. Right now, we're looking at what's bonded to the ring. Maybe it doesn't say that, but we're looking at what's bonded to the ring. We will, I mean, good questions. We'll see some of these. You're asking about multiple substituents. What you asked there, I'll kind of show at one point how there's some minor differences. At this point, let's draw some resonance structures. Resonance structures can be drawn when you have the intermediate. They can also be just drawn of just your starting neutral compound. Draw resonance structures of this. Okay, back in Organic 1, when we introduced resonance structures, I had a sub portion about neutrals, neutral compounds, lone pairs. I recommend you pull the handout back out. And on that portion, it said, when you have something like this, you start with what? The lone pair. Lone pair is a great place to start with resonance. Okay? That's what we discussed in Organic 1. Look at the handout. Okay? These electrons, move them in here, push these out. What do you get? It's now plus. We didn't do anything there or there. What's here? Lone pair and minus. There you go. When you have a lone pair involved in resonance, start with the lone pair, moving your electrons. You can continue on. These electrons can move here. These move out. What do you get? Get that there. And then these electrons can move here, move pi bond out, and you get this here so I can look at the structure. There's your resonance structures. The resonance structures tell you where the electron density of the oxygen ends up via resonance. Which carbons in the ring take on partial minus charge? Describe the carbons in terms of ortho, meta, para. Ortho to the group, para to the group. Yes. Ortho and para have the high electron density. Okay? What type of charge did this group impart to the ring via resonance? Negative. Donation. Okay? We'll do this later of the intermediate, and we'll actually stabilize the cation by this donation. Importantly, though, that's partial minus, partial minus, partial minus, if we should kind of think of hybrids, and where the charge that we get from resonance actually ends up. When we get over to directing effects, a methoxy is going to be said to be an ortho-para director, because it donates electrons to the ortho and para positions by resonance. You need to be practicing your resonance structures. Lots of resonance in your aromatic chemistry. I'd recommend, if you have any organic one, pulling out the resonance handout. Okay, that's group one. Group two. Group two are still activators, but we call them weak activators. There's two types of these. Conjugated pi bonds. For example, here, I have this alkene. That's a conjugated pi bond. It's conjugated with the pi system of the ring. This is going to be a donator. We can draw resonance structures. We can get something like this. It's not as good because this carbon doesn't have an octet and it's a carbocation. It looks like a primary carbocation. But it still is some donation. Now I'm going to show you a sigma complex. This is an intermediate in, for example, a bromination. And we form a positive charge. Can you envision this alkene stabilizing this positive charge? We know you can get resonance from over here. Any aromatic reaction, you're going to get resonance from the other pi bonds in the ring. We're talking about the substituent though. Can this stabilize the plus? Yes, by resonance, as shown. Windshield wiper it over, and we stabilize the carbocation, we delocalize it. Now it's not great because we're making a primary cation, but it is some delocalization. It's not great, that's why this is a weak effect. Not as strong as like the oxygen donating. The more commonly discussed one here though is your alkyl groups. And that's going to be your inductive donation, like toluene. Okay? What is its net effect? It's an sp3 carbon, that's sp2. So what do we know about sp3 carbons? They donate. Does this do anything by resonance? No. So all you have here is donation. So the net effect is donation. That's sort of shown below. We do a sigma complex. Maybe we do an iodination and we add it para. And that gives a cation here. Then we can do resonance. We can always do resonance in the ring. And we get here, here. We get that. We can, of course, do another resonance structure where we move these up and put cation here. I'll go ahead and show that. But is the methyl doing anything here at all? And what structure can you point to illustrate that? Which one can you really point to? Why do you like this one in?
It just skips by it, like with the oxygen would double down to that cation line to support it, or just could have interacted with it in any way. And since it goes there and doesn't interact with it, it sort of illustrates that the methyl has no resonance contribution.
Yeah, but what type of contribution does the methyl have?
Inductive effect, stabilizes the positive.
Right. Look at the stability of this. If I get rid of the methyl, is the stability not changed? Or if we add a methyl, does that stabilize it? Now this is just like primary, secondary, tertiary cations. With the methyl there, it's going to be more stable. And we can illustrate that right here with this resonance structure. This is what we're talking about. A methyl it stabilizes by induction. It's illustrated right here. Not by resonance, but by our old-fashioned induction. And yes, toluene is more reactive than benzene towards nitration or bromination because of that illustrated point right there. Okay, so your alkyl groups are sort of the most common of group 2. Group 3, these are actually withdrawers and deactivators. Halogens are the most common. You remember group 1 we exempted the halogens? Well, they actually fall here. They have a lone pair, but they're halogen. Now, chlorine's more electronegative than carbon, so it's withdrawing inductively. It can also donate by resonance. Just like we did with the methoxy, we can use a lone pair and do resonance and get something like this. But with halogens, it turns out that the withdrawing is the major effect, because they tend to be so much more electronegative. Inductive withdrawing is the major effect. So the net effect is withdrawing. And so, you can just go back here. It's not being drawn, but what if we drew, for example, a bromine here? Yes, that can donate by resonance. But what do we know about the net effect of a halogen that was just stated? The net effect is withdrawing. And so does that stabilize that cation? No. So because of that, something like bromobenzene, chlorobenzene is actually less reactive than benzene towards EAS reaction. The fourth group is your strong deactivators. This is going to be when the ring is bonded to electron poor atoms that have no lone pair. As they have no lone pair, they can't donate by resonance. That's not strictly correct. Because we saw an alkene donate by resonance, it didn't have a lone pair. But they will not donate by resonance. The only thing that they can do is withdraw inductively. Since that's all they can do, the net effect is what? Withdraw inductively. What type of groups? When we see these types of groups, for example, a nitro group is one type. If you draw your nitro, and you know your Lewis structure, first off, does that atom have a lone pair? No. So it's not group 1. You're never going to do pi bond resonance because you would never leave the oxygen without an octet. Basically, nitro is a classical group 4, which is what? Electron poor atom with no lone pair. Would you consider that nitrogen electron poor? Yeah, it's got a positive charge. And it does not have a lone pair. Classical there. Your sulfones. That sulfur is electron poor because of the oxygens. Also does not have a lone pair. Your ketones. Okay? The carbon, no lone pair. But it's also electron poor because that oxygen is pulling. We can draw partial plus on it. Nitrile group. Partial plus because of the dipole of nitrogen. So it's electron poor with no lone pair. Those are your common, these are all known to be sort of strong electron withdrawing groups. They're deactivators on the benzene ring. Let's review here. All these are listed as more reactive. Phenol. Okay, I gave you 4 groups. What group is the OH? Group 1. Has a lone pair and it's not halogen. Group 1. Strong activator. Toluene. It does donate, but it's not as strong as by resonance. So that's group 2. Not as reactive as phenol. All right, here's benzene. Bromobenzene is less reactive than benzene because its net effect is what? Even though it can donate by resonance, its net effect is withdrawing because it's so electronegative. Then we can get out here to maybe this ester. Okay, this is a carbon. Does it have a lone pair? No. Is it electron poor?
Yeah.
Yes, because of the withdrawing of the oxygen, that carbon's electron poor. So that sounds like it's group what? 4. Group 4. It's less reactive than bromobenzene. Because bromobenzene, at least the bromine can donate by resonance. That's not its major effect, but it does donate some. That's not going to donate by resonance. So an ester, is an ester with a deactivator or activator? How about this ester here? That's an ester, right?
Yeah.
Is it an activating group or deactivator for the ring? Deactivator. Are all esters deactivators? Why not? What functional group is this? Also an ester. The difference is in this ester, the oxygen's bonded to the ring. So look at the atom bonded to the ring. What type of group is this? Oh, it's got a lone pair, but it's not halogen. That's actually group 1. So this is actually an activator. So you can't just say all esters are deactivators. It depends on how the ester is arranged. Question?
So does it, actually, no, answer my question.
I was hoping you were about to ask something that I was going to allude to. Question?
Back on group 1B, or no, 2B.
Alkyl?
Well, I'm not entirely sure. You mentioned stuff about the resonance. We worked through that resonance. It was at the end of group 1. We worked through the resonance. If we were going to add a halogen to group 1, does the resonance take place before we add the halogen, or do we add the halogen and then do the resonance?
Resonance is always there. Resonance is not a step. It's sort of like pink, color pink. It's never red or white. It's pink. The hybrid's always there. It's just we show red and white because pink is hard to show.
I guess what I'm driving at is
If you do a mechanism, do you want to show the resonance first?
right.
It really doesn't matter. But what I will do is we will show the sigma complex first and then do resonance.
Okay.
But it's also important for you to realize that you can do resonance of just your starting material. And it illustrates where the partial minus falls. And so that can help explain when we get over to directing effects why the groups actually are ortho-para. In the end, guys, we will sum all this up and answer questions like that. We're sort of just kind of building the knowledge base right here for a little bit. Okay, we'll actually come back to that a little bit over there. I think on another handout is, which is more reactive? Do you think phenol or this? First off, they're both group 1. Oxygen with lone pair, oxygen with lone pair. Which one do you think can donate more though? Why? But this does have something pulling the other way. I mean, who can give you more money? A gazillionaire or just a millionaire? A gazillionaire is going to give you more money. Okay? They're both group 1, but we can make an argument that this guy's going to donate more. Okay? Okay, here's some rates. We're nitrating last week in lab. Benzene is right here. Toluene is 25 times faster at nitration than benzene. Why? It's got this slight donating group. It donates by induction. What is the name of this? Anisole. Anisole is 10,000 times faster than benzene at nitration. Typically when you nitrate anisole, you don't need a catalyst. Fluorine is also pretty reactive. Even though it doesn't have a methyl, one ring is activated by the other ring, really. And it actually does have a donator. If you look at fluorine, that one sp3 carbon donates. Nitrobenzene, if you try to nitrate it again and make dinitro, it's actually pretty tough to put another nitro group on because the first one is a deactivator and it makes the next nitration 100,000 times slower than if it wasn't there. What if you have multiple substituents? Kasha? It's pretty much just additive. You can just assess it, add them up. Of these 4 here, which one's going to be the most reactive? And guys, you have to be careful when you just say most reactive. You've got to clarify what you're talking about. Most reactive towards what? An EAS reaction. We're covering EAS right now. When we start doing a different mechanism, these effects actually reverse. So when you make a statement, make sure you say most reactive towards EAS. Which one would it be?
Second one.
I think it's the second one because we have here what? Strong activator, that's group 1. What is this? Weak deactivator. Okay. Well, how about over here? All it has is strong deactivator. Well, that's not going to be better than this. What about this? Right, they both have weak deactivators, but what does this guy have? So that's going to make it overall more reactive. What about over here? That's a strong deactivator and a weak activator. Or I could have said a weak donator and a strong withdrawer. So is that better than this? No. How close is it? It's not really that close if you look at it. Basically, you just sort of add them up, assess them. If there's any questions about that, let me know. Let's see what we're looking at next time. Basically, there's a handout from a textbook. You'll see that they group them a little bit differently. Okay, we'll explain that next time. The next time we'll be looking at directing effects. That is, if you have a group, where does the new group end up compared to the original? Please be looking ahead at that, doing some reading, and then we'll move on to Friedel-Crafts reaction probably Monday as well. Have a good weekend, guys. See some of you this afternoon.